Hello everyone, welcome to new class. Today's class is about network functions. So, in the network functions, we have to study about the standard input signals, also called singularity functions. And about these standard input signals, we have already discussed about in the control systems. So let us discuss about these singularity functions in briefly. Singularity functions are continuous time functions and their derivatives except one are also continuous. Singularity functions can be obtained from one another by successive differentiation or integration. And there are some standard input signals or singularity functions, and they are step signal, ramp signal, input impulse signals, etc. So let us study about these signals briefly. So first one is step signal, and step signal is defined as fs of t is equal to 0 for t less than 0 and is equal to k for t greater than 0, where k is the amplitude of step signal. So k is the amplitude of the step signal, and if the value k is equal to unit or 1, then the step signal is called unit step signal. So for the unit step signal, it is defined as u of t is equal to 0 for t less than 0 and equal to 1 for t greater than 0. And it is represented like, so this is the representation of the step signal. So here this is step signal for the amplitude k, and for k equal to 1 it is like this. Next is ramp signal, and ramp signal is defined as fr of t is equal to 0 for t less than 0 and equal to k into t for t greater than or equal to 0, where k is the slope of the ramp signal. And here also, if the value of k is equal to 1, then the ramp signal is called unit ramp signal. So unit ramp signal is defined as r of t. So this is fr of t, and here this is r of t is equal to 0 for t less than 0 and equal to k equal to 1 for unit ramp signal. So here we will get t for t greater than or equal to 0. And ramp signal is represented like this. So here this is slope is, here the slope is tan theta, and this is for unit ramp signal representation. Here k is equal to, that is the slope is equal to 1. Next is impulse signal. Impulse signal is defined as f delta of t is equal to 0 for t not equal to 0 and equal to a for t equal to 0. And here a is the area of the impulse signal. And if the value of a is equal to 1, it is called a unit impulse signal, and it is defined as delta of t is equal to 0 for t not equal to 0 and equal to 1 for t equal to 0. And this is the representation of impulse signal and the unit impulse signal. And here its area is a. Here the area of unit impulse signal is 1. The relationship between step signal, impulse signal and ramp signals are: derivative of step signal is impulse signal and derivative of ramp signal is step signal, or we can say the integral of impulse signal is step signal, integral of step signal is ramp signal. So these are the relationship between step, ramp and impulse signals. Next is exponential signal. It is defined as f of t is equal to 0 for t less than 0 and equal to k into e raised to minus at for t greater than or equal to 0, where a and k are real constant and a, the inverse of a, that is 1 divided by a, is called time constant tau. The time constant is the time taken to reach 63.2% of the total change from initial to final. So, the time constant is the time taken to reach 63.2% of the total change from initial to final, and this is the representation of the exponential signal. Next is sinusoidal signal. It is defined as f of t is equal to 0 for t less than 0 and equal to Vm sin omega t for t greater than or equal to 0. Vm is the peak amplitude and omega is the angular frequency in radian per second, and this is the representation of sinusoidal signal. Next is gate signal. The gate signal is defined as a rectangular pulse of unit height starting at t equal to a and ending at t equal to b. So, gate signal is defined as the rectangular pulse of unit height starting at t equal to a and ending at t equal to b. It is represented by GAB of t equal to u of t minus a minus u of t minus b. And if the gate signal is starting at origin, then it is represented like this one, and it is GOA of t equal to u of t minus u of t minus a. So, if the gate signal is starting at the origin, then it will be represented like this, that is G O 0 a of t equal to u of t minus u of t minus a. So, these are the singularity functions. Next is network functions. Network function gives the relation between transform of the excitation to the transform of the response. So, network functions gives the relation between transform of the excitation to the transform of the response, and these are the network functions: driving point impedance, driving point admittance, transfer impedance, transfer admittance. So, impedance, we know it is the ratio between voltage and current, that is V divided by I, and admittance is the reciprocal of impedance, that is I divided by V. And there are some relationship between that ratios, and that are called the network functions, and that are driving point impedance, driving point admittance, transfer impedance and transfer admittance. So, in the case of resistor, we have V of t equal to I of t into R, and here we are taking the Laplace transform to do the network functions. So, we have to take the Laplace transform here, that is V of s equal to I of s into R, and here the transform impedance is, that is transform impedance in the case of resistance is R. So, transform impedance is equal to R in the case of resistor. In the case of inductor, we have the voltage across the inductor V of t is equal to L into d I of t divided by dt. So here the transform impedance is equal to L into S. That is after taking the Laplace transform. And in the case of capacitor, we have V of t is equal to 1 by C into integral I dt. So here the transform impedance is equal to 1 by Cs. So that is in the case of resistor, inductor and capacitor. This is one port network and this is two port network. A pair of terminals at which a signal may enter or leave a network is called a port. A port is defined as any pair of terminals into which energy is supplied or from which energy is withdrawn or where the network variables may be measured. For a two-terminal pair network, two currents and two voltages must exist. So, here only one voltage and one current will be there. Here 1 dash is called the port, and in two port network 1 dash and 2 dash are called the two ports, hence called two port network. So this is one port network and this is two port network. And in two port network, if the driving source is connected across 1 dash, then the load is connected across 2 dash. Otherwise, if the source is connected across 2 dash, then the output is taken across 1 dash. For the one port network, the driving point impedance is defined as Z of S is equal to, here it is V of S divided by I of S. Then what will be the driving point admittance? So driving point admittance is Y of S equal to 1 divided by Z of S, and that is I of S divided by V of S. So this is the case of one port network. So in one port network, driving point impedance is V of S divided by I of S, and driving point admittance is I of S divided by V of S. Now in the case of two port network, the driving point impedance at the port 1 dash. So driving point impedance at 1 dash is represented by Z11 of S, and it is the ratio of transform voltage at port 1 dash to the transform current at the same port, that is V1 of S divided by I1 of S. Similarly, the driving point impedance at the port 2 dash, that is represented by Z22 of S is equal to, it is the transform voltage at port 2 dash to the transform current at the same port, that is V2 of S divided by I2 of S. Next is driving point admittance. So driving point admittance at the port 1 1 dash represented by y11 of S is reciprocal of driving point impedance, that is I1 of S divided by V1 of S. Similarly, driving point admittance at 2 2 dash is represented by y22 of S, the reciprocal of Z22 of, that is I2 of S divided by V2 of S. Next is transfer impedance. It is defined as the ratio of the voltage transform at one port to the current transform at the other port. So, we have Z21 of S is equal to V2 of S divided by I1 of S. So, transfer impedance is the ratio of the voltage transform at one port to the current transform at the other port. Similarly, we have Z12 of S equal to is V1 of S divided by I2 of S. Next is transfer admittance. It is defined as current transform at one port to the voltage transform at the other port. That is Y of S equal to I2 of S divided by V1 of S, and Y12 of S equal to of S divided by V2 of S. That is the ratio of the transform at one port to the voltage transform at the other port. Next is voltage transfer ratio. It is the ratio of the voltage transform at one port to the voltage transform at the other port, and represented by G21 of S, V2 of S divided by V1 of S, and G12 of V1 of S divided by V2 of S. That is the ratio of the voltage transform at one port transform at the other port. Similarly, current transfer ratio. So, what is current transfer ratio? It is the ratio of the current transform at one port to the current transform at the other port, represented by alpha of S equal to I1 of S divided by I2 of S, and alpha 21 of S, I2 of S divided by I1 of S. That is the ratio of the current transform at one port to the current transform at the other port. So, these are the network
And these
functions.
network functions are found by forming the system of equations using node or mesh analysis, and taking the transforms of equations by setting the initial conditions to 0 and solving for ratio of the response to excitation. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.